Welcome to today's lesson, and where we're going to talk about free water deficit. And just so you know, the free water deficit, which looks very similar to the free water clearance, these are not the same entities at all. So hopefully you won't get the nomenclature confused. So what is the free water deficit? It's basically the amount of water that a patient has lost that you have decided you want to replace. How do you know how much water someone has lost? Because most water is stored in the intracellular space. And we don't have readily available measurements to tell us what's going on in the intracellular space. So we need a surrogate, something that's easy to measure, that's in the extracellular space, that tells us what's happening with water in the intracellular space. And that surrogate is the concentration of sodium in the serum. So the concentration of sodium in the serum is not what we call volume, which is what many people commonly confuse it as. This is not equal to the word volume, but rather equal to the word water or free water. So anytime we have water overload or a water deficit, we're going to have some change in the concentration of sodium that's in the serum. That's what's going to tip us off that there's something wrong. So let's try to use this measurement to determine how much water someone has lost in this particular example, or in this lesson that we're discussing. So, say we have a concentration of sodium in the serum, and it's a very high concentration. We can say 150, 160, for example. So we want to know how much water does someone need to take in, drink, or receive by IV fluids in order to bring that concentration of sodium down to a new concentration, what we're going to call concentration of sodium in the serum desired. Now the desired concentration is whatever you want it to be. And the concentration of sodium here is what it is when you see the patient. And again, we're focusing on the concentration of sodium because we know that when the concentration is high, you have a water deficit. And when the concentration is low, you have water intoxication. So in this case, we have a concentration that's very high, a deficit of water, and we want to know how much water to give to get it down to the level that we desire. So keep in mind one more point, that water or water balance does not affect the total body sodium. In other words, the total milliequivalents of sodium that this patient has at this state here is equal to that same milliequivalent sodium in this desired state here. So we can mathematically represent that. We can simply say that the total amount of sodium in your body when you first walk in the door is equal to this. This is going to give you milliequivalents of sodium. And that's this condition right here. That's this scenario. That's going to equal your desired concentration of sodium times something, your total body water, but you're going to add some water. So if you rearrange this equation, you'll be able to solve for x, and x represents your free water deficit. The amount of water you have to add to the patient right here in order to get this desired concentration of sodium here. In other words, to get that water into the intracellular space and to know that it got there, you want to reach this desired sodium. Now, X has a few caveats that are critical for you to know, so let's go through that. X is the free water deficit. and we just calculated that on the last slide. But there's some things you have to know about this. Number one, x is not a static value, which means whatever you get for x today is not going to be the same thing you get tomorrow. So x is only valid for that point in time. 2, and most importantly, x does not take into account ongoing water losses. So you could have a patient who is still losing water at a very high rate, and x would not reflect that right away. So you would not know how much extra water to give because you don't have that value incorporated in x. All x tells you is what the deficit is. It doesn't tell you what the deficit is going to be at any point in time down the road. So when you calculate the free water deficit, you have to interpret this in a cautious way. You have to say to yourself that at the minimum, the patient has an x liter deficit of water. Now there could be a greater deficit because there may be more water being lost as time goes forward, and so you have to account for that. And the best way to account for that, I will show you, and we've already discussed this in another lesson, is the free water clearance. So if you add x, which is your free water deficit, to your free water clearance, you're going to get a more accurate picture of how much water the patient is losing. Now this might be a little difficult calculation to do, but for this lesson, all you have to know is that x, which I showed you how to calculate, it's pretty simple to get. It's not a static value, so it's going to change as time moves forward, and it doesn't account for what you're losing, so you're going to have to rely on the free water clearance to get that information. But that's it. That's how you get the free water deficit. Thank you.